Kids in Ohio are like, what just happened? Extended product rule. We take the derivative of the first times the second times the third, plus the first times the derivative of the second times the third, plus the first times the second times the derivative of the third. How many guys had extended product rule? Good. Okay, quotient rule. Low d high minus high d low, low, low. That better be everybody in the house. The chain rule, this was the new one from yesterday. How does that work again?
Some babies.
There's some babies and there's some mamas going on here. Floor, what do we do?
Oh, I was going to ask about the one. It's a plus, right?
No. Low d high minus high d low, low, low. Chain rule. There's some babies and some mamas. Evel, how does the chain rule work?
The derivative of the mama
Derivative of the mama.
times the baby
I disagree.
of the baby.
Okay, first of all, the mama, the baby, which one's which?
Oh, the mama is the F.
The mama is the outside function. The baby is the inside function. What the chain rule said, you take the derivative of the mama, leave her baby alone. So it's f prime of g of x now times the derivative of the baby. We looked at a couple of examples of that yesterday. And then the extended chain rule, a function inside of a function inside of another function. I think you guys know what to do here.
F prime.
Start with f prime. You're taking the derivative of that big mama and leave her babies alone. F prime of g of h of x. Paul? Then you multiply by the derivative of g of h of x times h prime. Those are the 12 derivative rules that you are expected to know and know cold at this point. It should not be a place for like deep thinking. We need to know them. Yeah. Yes. All right. If all goes well in the next 20 minutes, I've got 5 new derivative rules for you. Yay! Yay! Good answer.
17.
Karina, are we filming? Okay. So you guys are going to need your calculator for this first one. I want to look at the derivative of the natural log of x. We're going to build it. This is not going to be considered a proof of the derivative rule. Proofs are good, proofs will come, but not today. Your brains are not ready for the proof yet. If we did the proof, tears would start. And we don't need tears. So instead, you guys are going to use your smarticle particles. And we're going to use calculator a little bit. Okay, we've got the graph of natural log of x up here. Down here, we're going to build the derivative. And you might be thinking, gosh, didn't we do stuff like that in the last unit? Yes. Yes, we did. What I'm looking for are things that we know about the graph of f and what that means about the graph of the derivative. So, for example, I've got one started over here. Because the graph of f is increasing for all values of x greater than 0, everybody's okay with that?
Yes, sir.
We can see the graph is increasing?
Yes, sir.
What do we know about f prime?
It's above the x-axis.
F prime is positive for all x's greater than 0. If I'm Sylvia, I might say above the x-axis for all x's greater than 0. That's true. Because f is increasing, f prime has to be positive. Anybody see anything else about the graph of f and what it tells you about f prime? Take a minute, talk to the friends near you. There's at least 3 or 4 more things that you should be able to tell me because you see the graph of f. What do you know about f prime? Talk to the friends around. Okay, how many groups have at least one more thing that you can tell me about the graph of the derivative? 2 groups, that's it? Oh, come on. 3, 4, 5. Sylvia, tell me something else.
There is a vertical
We'll say the right word.
Don't just.
Asymptote. This guy has a vertical asymptote. F has a vertical asymptote at x equals 0. So what? So what? F has a vertical asymptote. F prime has a vertical asymptote. F prime has a vertical asymptote at x equals 0. How many guys had that? Okay, some, not as many as I was hoping. What else? What else? Jose, what else?
Convex is concave down.
Oh, good. F is concave down. Where? On what interval?
0.
Everywhere.
Everywhere.
Everywhere, you're right. F is concave down for all x's greater than 0. So the thing that we know about F prime, F is concave down, so F prime has to be decreasing. F prime is decreasing for x greater than 0. There's at least one more thing I'm hoping somebody's going to notice. Karina.
There's a root at x equals 1.
There is a root at x equals 1, but roots of the function don't tell you about F prime.
Okay.
Roots of the derivative would tell you about horizontal tangent lines. Jackie, what else?
It's a relative minimum because it's from negative to
You're going in the wrong direction.
oh, it's
Okay, hold on, and stop saying it. I heard you say it. I think you mean this function here is changing from negative to positive.
C.
Okay, now we're switching languages. Totally confused. F is changing from negative to positive, but that doesn't mean the derivative has a minimum. What function has the minimum? Little f changes negative to positive. The antiderivative, the guy that came before this, would have the minimum. I want to talk about f prime. There's one more thing, and don't say horizontal asymptote. Flora?
Yeah, that function has a relative max.
Where do you see the function having a relative maximum? No, I'm just curious. Where do you see it?
And I think it's
At the what?
at the end of the picture they gave you.
At the end of the picture, but here's the thing. You guys know what the graph of the natural log of x does.
Oh, wait.
It continues to increase. It never actually decreases, so there's no relative maximum. There is something, though, that happens as x approaches infinity. F of x starts to, I'm just going to say, flatten out.
So it has the horizontal.
No, not saddle point.
It has the horizontal.
Not a horizontal asymptote, but the graph is still increasing. That's why there's no horizontal asymptote. But the tangent lines are flattening out. So what does that mean about the derivative?
Is approaching 0.
That means f prime of x is going to approach 0. Take a minute, pull all those thoughts together. Sketch the derivative for me. The derivative is going to be positive. The derivative is going to have a vertical asymptote. The derivative has to be decreasing. The derivative has to approach 0. I wouldn't use the markers yet, though. Here, get the phone. Okay, most folks seem to have sketched pretty much the same thing. I'm seeing a lot of graphs that look something like that. This is what it has to look like. Above the x-axis, a vertical asymptote, decreasing, getting close to 0. So my next question for you all is, anybody recognize that? Is that a graph that you know?
So what is it? Winter Ridge?
Oh my gosh, it can't just be Henry. Look at that parent function survival guide if you need to. There are functions that you know that look like this. Jackie?
E to the power of kx.
E to the power of kx, where k is negative or positive?
Negative.
Negative. If it's decreasing, it would have to be a negative. There are other parent functions that have this behavior. There are others that you need to know. Oh, I won't tell you. I have high expectations, and you have the things that you need. There's at least 2 others that I was hoping people are thinking about right now. Eval, what you got? Okay, the graph of y equals 1 over x has that behavior. And Jose?
Y equals 1 over a squared.
The graph of y equals 1 over x squared has that behavior. These are my suspects. I suspect, and maybe there's others, but I suspect that the derivative might be one of these because it has the right behavior. Are we okay? All right, let's take out the calculator. Paul, can you drive? Okay, thanks. So Paul's going to drive. And this, again, not a proof. Don't go to college and say you proved it. You didn't. All right. On your calculator, please graph the natural log of x. Start with the graph of the natural log of x. Nice. Now what I want to do is I want to graph, Chris, you're going to graph, right? I want to graph the derivative. I want to get the calculator to do the work for me. So what were those skills? What were those buttons? Okay, Paul's going crazy. First of all, you need to get a new function in there. I want the calculator to graph the derivative for me. So it's the templates button. It's the one next to what I like to think is the Bible. Okay, the templates, we hit the derivative. Just give me a quick thumbs up if you get this as your derivative. Your calculator sketching. I see 1, I see 2, I see 3, I see 4, 5, 6, 7. Looks like 8. I want to wait for some everybody else. We've got to get the graph. Gonzalo, you're good with the graph? Jesus almost has the graph. Now here's the thing. Does that match our sketch?
Yes.
Absolutely matches our sketch. Do we know what function it is? You still don't know what function it is, but we have our suspects. So, let's graph the suspects. So let's hit tab again. And the first one I heard you guys graph with recommend is e to the negative x, Paul. So graph e to the negative x. E to the negative x. Is that the derivative?
No.
Is everybody okay that that's not the derivative? If e to the negative x was actually the derivative, it should be exactly the red graph. So, give me one of the other suspects.
1 over x.
Okay, 1 over x. 1 over x. Here comes the new one, 1 over x. Is it a perfect match?
Oh, yeah.
Yes.
Is it a perfect match?
No.
No, because it has no.
Sylvia, why are you saying no? Because of this part over here? Now here's the thing, the graph of the natural log of x has a domain restriction. I can only use x's greater than 0. If I restrict myself to the part of 1 over x where the x's are greater than 0, does it appear to be a perfect match?
Yes.
Okay, perfect. So that would be my visual argument that the derivative of the natural log of x is 1 over x. This isn't a proof. Don't fall for it. There's going to be a proof, but this is my way of getting you to sort of embrace the fact that the derivative of natural log of x is 1 over x. Yes, sir?
Why isn't it a proof?
A proof, if you're not crying, it's not a proof. We're going to do a proof, you'll feel it. You'll feel the fact that we're doing a proof. All right, so here's what we're going to do. Groups 1, 2, and 3. You guys are going to repeat this process. You're going to do, Paul, you're done. Thank you so much for your service for our country. Groups 1, so Jesus, Julissa, Sylvia's group. You guys are going to repeat this process with the graph of sine of x and with the graph of e to the x on the back page. Groups 4, 5, 6, you guys are going to repeat this process with the graph of cosine of x and the graph of e to the negative x. So start by looking at the graph. What are the things that have to be true? Come up with your sketch. Then see if you can figure out which one it is.
Cosine.
you know that this is gonna be, it's gonna be like coast. It's gonna be like coast graph.
Okay, but you're starting with the sketch. Don't start with the calculator. I want to hear conversations about, oh, the graph of sine has a horizontal tangent line, so the derivative behaves a particular way. Sheila.
Because, well, sine and cos, remember, they can switch.
Christopher. Eval. Laura. Michelle. Henry.
It means you native. You got
Melissa.
So let's use the and then sine, cosine. Oh, I did it wrong. We know it's cosine. I mean cos.
Chris, what are the things that we know about the derivative? Looks like you figured out where you're going to have some roots.
Yeah.
I agree. What's going to be positive?
The negative.
The slope.
Okay, what does that tell me about the derivative?
Oh, it's above the x-axis.
Sure. I mean, we know it's cosine.
Okay, for that first part, from like negative 2 pi to negative 3 pi over 2, your derivative has to be above the x-axis. I agree with you. Why?
Because it's above the x-axis.
Because the graph of sine of x is increasing. Because the graph is increasing, the derivative has to be positive. Once you've got your sketch, try it on the calculator. See if you can figure out exactly what the derivative graph is supposed to be.
I don't know what it's
You know what cosine looks like?
see.
I really think it's fine though.
Well, cos, remember, it starts with the top.
Wait, what?
Let's graph
The max and the minimums.
She's wrong.
I wouldn't change this from
It's because look, it looks like the same.
That's your sketch.
That's why I said it's cos.
It's gonna be the roots and the derivative.
But we did the graph.
Does it go like that? Like a W?
Yeah.
You guys, all three of you have a great sketch.
Oh, no.
You've got good sketches, they're good curves. And you figured out what was happening.
Can be fine.
Yeah, but she said that like that's one we did.
Okay, I've only given you a particular window, a particular slice of the graph. But there's something that
Pretty soon.
let me believe
Maybe
in
like
the graph.
9.5.
Okay, I'll try secant, it's not secant.
So that's a cos.
You guys all have great curves here. Have you
Not
figured
like,
out?
it's there design, but just flip.
I tried starting it.
Like how you flip. So you
Based on what you've done,
Way to flip
later,
So
we
the thing is, this is
sine of x is.
What? Hey, somebody else.
this is
What are you doing? Why are you doing
I think it's my second.
Friends over here, how we doing?
No, because the other 10 to 10.
Have we figured out what that graph is?
look, there's no look.
Oh,
Big
The rear rating.
2 minutes!
wait a minute.
Then cos will be negative.
Hi friends, how we doing?
I should have just turned it.
We
right?
Oh, good, memory.
Is this like
We've done this months before, and you found it.
Is that?
So what graph is this? And have we checked it on the calculator? And it is a perfect match. So the next time I ask you what's the derivative of sine of x, you're going to tell me it's the cosine of x. No, it's not negative cosine of x. Okay, so now you guys should be working on the graph of e to the x. Okay. Haven't figured it out yet?
You need to identify what
Think about it. We have this graph, and this is thick. Then we have the little one, which is cold. Then it's cold.
Oh, you want to end.
Right here looks exactly like this.
That's
The root of this.
Why is this hard? It's because we don't know the path. You got your stuff.
Oh, you're in my heart. Or on the test.
There's some grade right now. That's in the grade. That's fine.
What do you mean?
Alrighty. I knew we were going to have to go fast here. Most of you guys seem to have figured out at least one of them. I want you to get this in your notes, please. If all went well, we've discovered that the derivative of sine of x is cosine of x. How many of you guys honestly came up with that? Okay? However, the graph of derivative of cosine of x is negative sine of x. Not sine of x, it's the negative sine of x. If you sketch the graph starts to decrease at x equals 0, which is the opposite of the behavior that you want. Hold on, Henry. Okay, we're going to continue talking about these tomorrow. The graph of e to the x, if I look at its derivative, is e to the x. It's exactly the same. The derivative of e to the negative x is the opposite. It's negative e to the negative x. So we now have 5 new derivative rules that you need to know. Derivative of sine of x, everybody can tell me is?
Cosine.
Wait, everybody can tell me is what?
Cosine.
Cosine of x. Derivative of natural log of x is?
1 over
1 over x.
1 over x. Derivative of e to the x is?
E to x.
E to the x. It's the same. Derivative of e to the negative x?
Negative e to the x.
Negative e to the negative x, and the derivative of cosine of x?
Negative sine x.
Is negative sine of x. Oh, and derivative of tangent of x? Oh, we don't know that yet. How about the arc tangent of x?
I said that.
Oh, we don't know that one yet either. Bye-bye. Get your homework done. You do? What's the derivative of arc tangent of x? That was derivative of arc sine of x. Thanks for trying.